Hello everyone, welcome to module 13 of the course on application of spectroscopic methods and molecular structure determination. In this module, we will see some aspects of the variable temperature NMR technique and how to study dynamic processes in molecule by NMR spectroscopy at various temperatures. Now, NMR spectroscopy is a very powerful tool and it can be used for a study of several different types of dynamic properties of the molecules. Some of the dynamic processes are listed here, which can be studied by NMR spectroscopy. Now, conformational change, a chair form of cyclohexane going to another chair form, for example, can be studied by NMR spectroscopy. Bond rotations, carbon-carbon bond or carbon heteroatom bond rotating, the restricted rotation of this kind of bonds can be studied by NMR spectroscopy. When molecules tend to aggregate in solution, such an aggregation phenomenon can be studied by NMR spectroscopy. A typical example would be pi stacking aggregation of aromatic systems in solution. Finally, the fluxional properties of molecules can also be studied. A very classical example would be the fluxional property of bulvalene that has been studied by NMR spectroscopy. Now, the sample tube in the NMR spectrometer can be either cooled up to minus 150 degrees Celsius or it can be heated to plus 150 degrees Celsius. This 300 degrees window is accessible provided the solubility and the solvent melting point, boiling point permit such an operation. Now, if the temperature of the sample can be cooled to such a wide range of temperatures, then it is possible to study processes that has activation barrier typically in the range of about 8 to 25 kilocalories per mole can be studied using NMR spectroscopy. Now, let us look at the basic principle behind the study of variable temperature NMR spectroscopy for the dynamic processes of molecules. Now, assume the proton can exist in two possible chemical environments. The example that I would like to cite here is the proton in cyclohexane, which can exist either in the equatorial position or in the axial position. The equatorial position and the axial positions are distinctly different chemical environment as we have seen earlier. So, if NMR can, for example, distinguish whether a proton exists in the axial position or in the equatorial position, that will be a very valuable information in terms of studying the stereochemistry of cyclohexane kind of molecules. The ability of NMR to very clearly define the chemical shift environment of a proton and hence the chemical shift value of the proton will depend upon how long the proton is residing in that particular chemical environment. If it is residing, for example, long enough, then NMR will be able to tell the chemical environment to be either axial or equatorial. If it is too short, then also NMR probably will give an average value of the equatorial and the axial chemical environment positions. Typically, the difference between the two states of residence is very small, of the order of microcalories per mole. Therefore, the lifetime in any particular state should be sufficiently long enough in the NMR time scale to give the correct chemical shift value. The uncertainty principle is expressed here. Now, this is the uncertainty principle expressed in terms of the residence time or the lifetime in a particular state and the difference energy between the two states, let us say for example the axial and the equatorial states of a particular hydrogen that is being present here. There can be a very large uncertainty in the energy state depending upon the lifetime of the molecule in that particular state. So, the NMR signal can be either very sharp or very broad depending upon two types of conditions that is met. What are the two types of conditions? If the proton is exchanging between the two states very rapidly, then NMR will only see an average chemical shift value of the two states. The signal can still be very sharp signal in this particular case. Nevertheless, it will be an average chemical shift of the two states. If the proton is exchanging between the two states very slowly in the NMR time scale, the NMR will give only the individual chemical shift values of the two states. In other words, NMR can distinguish the hydrogen to be either in the axial state or in the equatorial state in the case of cyclohexane. So, two signals will be obtained, one corresponding to the axial, the other one corresponding to the equatorial state. Now, in between these two states, it's neither too fast or nor too slow. The uncertainty will set in terms of the determination of the chemical environment of the particular proton. As a result of that, in between states where the rate process is neither too high nor too low, there will be a large uncertainty. Broadening of the signal is what one typically sees in the variable temperature NMR spectra. Now, What makes the variable temperature NMR a very special technique? Because chemical rate processes can be controlled by temperature. The rate of a reaction can be controlled by a temperature, and hence the usefulness of the variable temperature NMR spectroscopy. Now let us take the first example of the study of dynamic processes which are based on conformational dynamics of molecules. A very classical textbook example is the chair-to-chair interconversion of cyclohexane. This has been studied thoroughly by NMR spectroscopy. In order to study this process, the cyclohexane D11 was taken. In other words, there is only one proton that is present in the cyclohexane. All the other protons have been substituted with the deuterium. So depending upon the kind of chair conformation that the cyclohexane has, it is either in the axial position or it is in the equatorial position. Now this study has been carried out by variable temperature NMR spectrum. The spectra are shown on the left hand side in this particular frame here. If you look at the NMR spectrum at minus 50 degrees Celsius, for example, which is already a low temperature process, NMR is unable to distinguish between the axial hydrogen and the equatorial hydrogen. What you see is only one signal corresponding to the average of the two states, namely the axial state as well as in the equatorial state. In other words, even at minus 50 degrees Celsius, the rapid interconversion is taking place, and in the NMR timescale, NMR is unable to distinguish whether the hydrogen is residing in the axial state or in the equatorial state. What it gives is an average signal corresponding to neither of the states of the hydrogen being present in the either axial or in the equatorial position. Now let us go to the other extreme. When the sample is cooled to minus 89 degrees Celsius, for example, what happens is you see two signals corresponding, one corresponding to the equatorial state of the hydrogen, which is at the higher delta value. This is about 1.6 delta ppm in terms of the chemical shift value, and the other one, which is coming at a lower delta value, corresponds to the axial position hydrogen, which is about 1.2 delta ppm or so. Now at this particular temperature, the interconversion of the two states is so slow that NMR is able to distinguish this particular conformer as the axial conformer and this particular conformer as the equatorial hydrogen conformer corresponding to the two states. Actually, there is no energy difference between the two states. The axial and the equatorial are essentially the same chair conformation. So they should exist in equal population of 1:1 ratio. And you can see from the height of the peak, both the peaks are nearly equal in intensity. Therefore, the area under each of the peak is going to be approximately same. So you have 1:1 mixture of the conformation wherein the hydrogen is in the axial position and another conformation wherein the hydrogen is in the equatorial position corresponds to the two lines that one sees in the spectrum. Anywhere in between temperature, there is a large uncertainty as to whether the hydrogen is existing in the axial position or in the equatorial position. NMR is unable to distinguish between the two positions, and hence there is a large uncertainty associated with the measurement of the chemical shift, which is reflected in terms of broadening of the signal. Now between minus 63 and minus 60, you can see there is a coalescence that is taking place. There are two peaks here which coalesces to only one peak at this particular temperature. So this particular temperature is known as the coalescence temperature. The coalescence temperature is important because several kinetic parameters can be obtained from the coalescence temperature. And above the coalescence temperature, of course, you see an average signal of only, if you take the chemical shift value of this will be exactly the arithmetic average of these two chemical shift values. In other words, you can see that it comes at midpoint corresponding to this particular chemical shift, two chemical shift value. Midpoint is corresponding to this particular chemical shift. And that is the average value of the axial equatorial conformational equilibrium being very rapid. Now let us take the example of the carbon-13 spectroscopy of 1,2-dimethyl-cyclohexane, particularly the cis isomer of 1,2-dimethyl-cyclohexane. The cis isomer of 1,2-dimethyl-cyclohexane should have one axial methyl group and one equatorial methyl group. Both the axial and the equatorial methyl group point in that same direction, and hence it is a cis isomer. If you want to refresh your memory about the dynamics of the cis isomer of the 1,2-dimethyl-cyclohexane, please refer to Nasipuri's book on stereochemistry of organic compounds. Now this particular molecule is a chiral molecule, and it doesn't have any kind of symmetry elements that is present here. Therefore, if this molecule were to exist in this particular form, then all the carbons that are present in this molecule should be distinguished chemical shift wise, and there should be 6 of the ring carbons, and 2 of the methyl carbons which are also chemically distinct. One is axial and the other one is equatorial. So one would see 8 signals in the carbon-13 NMR spectrum of such a molecule. Now what is the dynamic process that is taking place? The dynamic process is the establishment of this equilibrium of one chair form going to another chair form. In the process, actually what happens is one of the enantiomer gets converted to the antipode of the enantiomer. In other words, this is a process of racemization. Cyclohexane 1,2-dimethyl cis isomer of 1,2-dimethyl cyclohexane is an example where it is a non-resolvable chiral molecule. Non-resolvable because it rapidly undergoes racemization by going from one chair form to another chair form, which is a racemization process itself. Now, while going through this transformation, it has to go through a transition state which look very similar to the planar transition state. In other words, this chair form has to go to this particular chair form. At some point of time in the transition state, it has to sort of attain a planarity kind of a structure, which is this particular structure, and this structure has a plane of symmetry, as you can see in this molecule. So this would be an achiral system, whereas these two conformations would be chiral in nature. Now let us look at the carbon-13 spectrum. This is the depth spectrum. In other words, in this particular spectrum, the CH2 carbons will come as negative peaks, and the CH and the CH3 carbons will come as positive peaks in terms of the phase of the peak that is being seen. You can have a negative phase or the positive phase depending upon whether it is a CH2, in which case it is a negative phase, or if it is CH or CH3, odd number of hydrogen being present, then it would be a positive phase of the NMR signal. So as I said, if this molecule were to be existing in a frozen state without the conformational interconversion, there will be a 1:1 mixture of these two isomers, which are enantiomers. Enantiomers are indistinguishable by NMR spectroscopy. They are chemically equivalent, so their chemical shift value of this equatorial carbon and this equatorial carbon will be identical. So one should see 8 signal in the NMR spectroscopy, of which 4 of them will be CH2 type of carbon, 2 of them will be CH carbon, and 2 of them will be CH3 carbon. So if you see 4 signals which are in the negative phase, 1, 2, 3, 4, these 4 signals correspond to the CH2, and 2 of the CH and 2 of the CH3 will have positive phase. 1, 2, these are probably the CH carbons, and these are the CH3 carbons. So there are 8 signals that are seen in the NMR spectrum, carbon-13 spectrum of the cyclohexane. So variable temperature is measured in the carbon-13 NMR spectrum of dimethylcyclohexane in this particular case. This is the normal carbon-13 spectrum, whereas this is the depth spectrum. The depth spectrum is essentially recorded to distinguish between the CH2, CH and CH3 carbons. If you look at the normal carbon NMR spectrum also, you will see 8 signal. 1, 2, another signal is merged with this, 3, 4, 5, 6, 7th one is again merged, it is not resolved, so 7, 8. There are 8 signals that are very clearly seen in the NMR spectrum. Now let us assume that this is sort of not frozen, it is undergoing a rapid interconversion between these two states. If it is going to rapidly interconvert between the two states, the NMR is going to see the molecule as if this is a state that is being present, because this is very similar to a transition state structure between the two structures that are mentioned here. So if NMR sees a signal corresponding to a structure of this kind, where there is a plane of symmetry, then you should see only half the number of signals in the NMR spectrum. That is, one signal corresponding to the CH3 here, which will be identical to this CH3, one signal corresponding to this CH, and this would be essentially identical to this CH, one signal corresponding to these two CH2s, and one signal corresponding to these two CH2s. Indeed, when you look at the spectrum at room temperature, where there is a rapid interconversion of one conformer and the other conformer, NMR is unable to distinguish the axial equatorial methyls. So the methyls gives just only one peak in the NMR spectrum, which is shown here, for example. So the NMR spectrum should see 1, 2, 3, 4. Only 4 signals should be seen. So indeed, only 4 signals are seen in the high temperature NMR spectrum. What I mean by high temperature is at room temperature, where the rapid interconversion is taking place. At low temperature of, let us say, for example, 223 Kelvin or so, the interconversion is slowed down considerably, such that NMR is able to see the axial equatorial methyls separately, and the conformation gives this is a chiral conformation, so 8 different signals are seen in the NMR spectrum. So the molecule is a beautiful example of essentially a chiral molecule existing in two enantiomeric forms. The enantiomer being indistinguishable, you just see as if there is only one type of molecule in the NMR spectrum of the cis dimethylcyclohexane, 1,2-dimethylcyclohexane at low temperature, whereas at room temperature, close to room temperature, essentially you see the averaged out signal corresponding to 4 carbons in the NMR spectrum, because this would be the average of these two type of structures that you have in the NMR spectrum. Now, at the coalescence temperature, one can find out what is the rate constant of the reaction. The rate constant at coalescence temperature is given by this expression, where K, which is Kc, is the rate constant at the coalescence temperature, which corresponds to pi delta nu. Delta nu is the difference between the chemical shift values of the two type of system. If it is axial hydrogen and equatorial hydrogen, delta nu corresponds to the difference between the chemical shift value of the axial hydrogen and the equatorial hydrogen divided by root 2. So we can do a one-point kinetics and get the rate constant at the coalescence temperature using this expression, provided there is no spin-spin coupling between the two protons. If there is a spin-spin coupling between the two site exchangeable proton, then the coupling constant also gets into the expression. So at this point of time, the Kc would correspond to this particular expression that is given here. Now once you have Kc at the coalescence temperature, one can also calculate the thermodynamic parameter in terms of the activation energy of that particular process using this expression, using the NMR technique, which would be a one-point kinetic technique. Let us take another example of a chair-to-chair interconversion. It is not only cyclohexane that undergoes chair-to-chair interconversion. This kind of heterocyclic system where you have X is equal to oxygen or sulfur, in other words, it is 1,3,5-trioxane or 1,3,5-trithiane kind of molecules also undergo rapid interconversion from one chair form to another chair form. The chair form interconversion is denoted by the axial hydrogen being red here, which becomes equatorial upon chair-to-chair interconversion, and the equatorial hydrogen being blue here, which gets converted into the axial hydrogen during the chair-to-chair interconversion. Now, under the conditions of very slow exchange between these two molecules, the NMR spectrum is going to be seen as a single spectrum of this particular molecule. The axial and the equatorial hydrogens are attached geminal to this particular carbon. So they are going to be diastereotopic in nature. So they would couple with each other. So this coupling corresponds to an AB quartet kind of a signal in the NMR spectrum of such molecule. In fact, this axial hydrogen is same as the axial hydrogen over here and the axial hydrogen over here. The molecule has a C3 axis of symmetry, so it doesn't matter which one of the methylene groups that you take for analysis. Essentially, you will get an AB pattern at low temperature. At room temperature, when this is rapidly interconverting between the two states, of course, one cannot distinguish between the axial and the equatorial hydrogen. So essentially, one gets only a singlet kind of an NMR spectrum in the at the room temperature or at a higher temperature where the rapid interconversion is taking place. Now, based on the study NMR variable temperature NMR study, in the case of 1,3,5-trioxane molecule, the barrier for the flipping of one chair conformation going to the another chair conformation is very similar to the one that you see for cyclohexane, namely 10.9 kilocalories per mole. In fact, in the cyclohexane case, the 10 kilocalories per mole activation barrier is probably the most precise value that is ever determined using a spectroscopic technique for such a conformational dynamic processes. Now let us take the example of piperidine as a molecule. In the case of piperidine, the 3 position and the 5 position are deuterated, in other words substituted by deuterium, so that one can avoid the complication of coupling between this hydrogen and this hydrogen here in the NMR spectrum. So what is present here is a methylene group in the 2,6 positions and another methylene group in the 4 position that is present in the molecule. Now this is the methylene region of the NMR spectrum of piperidine molecule, and you can see here at a very low temperature of minus 85 degrees Celsius or so, there are 2 AB quartets seen here. One AB quartet has nearly twice the intensity of the other AB quartet. In fact, if you look at the hydrogen which are in the 4 position, this would appear as an AB quartet at low temperature when there is not a rapid interconversion between the two states. Similarly, when you look at the hydrogens in the 2,6 positions of this molecule also, you would see only a AB quartet corresponding to 4 hydrogen intensity. That is the reason one of the AB quartet is twice as big as the other AB quartet. So this AB quartet, which is in the 4 position, which is away from the nitrogen, has a lower chemical shift value, whereas the one that is adjacent to the nitrogen has a higher chemical shift value, which is this particular AB quartet. So you see two AB quartets corresponding to the diastereotopic methylene kind of a proton in a frozen state where there is no rapid interconversion between the chair to chair interconversion between the two states. Now what happens if you heat the sample up to about minus 40 degree where the rapid interconversion start to take place? The two AB quartet essentially collapse because you can no longer distinguish the axial and the equatorial position when it is rapidly undergoing interconversion from one chair form to the other chair form. So this AB quartet collapses to a singlet. This AB quartet also collapses to a singlet. This corresponds to the 4 hydrogens in the 2 and 6 position. This corresponds to the 2 hydrogens in the 4 position, which are these two hydrogens in this molecule. Now, such a dynamic process can also be simulated using computer simulation by putting in appropriate rate constants for the processes, and essentially one can simulate not only the low temperature and high temperature spectrum, the line broadening at the intermediate levels can also be precisely simulated in the NMR spectrum. And these are the simulated NMR spectra, and this corresponds to the experimental NMR spectra at various temperatures. Now you can go from here, for example, at low temperature. As you increase the temperature, at one particular point there is a coalescence temperature which is close to about minus 62.5 degrees Celsius or so in this particular case, and that coalescence temperature, the AB quartet essentially coalesces to a single peak. It is somewhere between minus 60 and minus 62.5 degree Celsius or so in this particular instance. These are examples of simple carbon-carbon rotation or restricted carbon-carbon rotations which can be studied at low temperatures. Now, normal temperatures, if you look at the tertiary butyl cyclopentane, there will be a rapid rotation between this carbon and this carbon. So, one will not be able to distinguish the 3 methyl groups of the tertiary butyl group at ordinary temperatures. However, if the sample is cooled to minus 150 degrees Celsius, it is possible to freeze the molecule from undergoing rapid interconversion of conformations. This is a Newman projection formula of these 2 carbons that are seen here. In other words, this carbon is in the front and this carbon is in the back side of the Newman projection, and the ring and the hydrogens are clearly shown of the cyclopentane ring, and the hydrogen that is attached to this particular carbon is coming here. Now, if you look at this particular picture, this is actually the Gaussian conformation or the staggered conformation of this carbon-carbon bond rotation. Now, if the carbon-carbon bond rotation is frozen, this is likely to be the most stable conformation because the bulky groups are far away from each other in terms of the position of the bulky groups. If that were to be the case, these 2 methyl groups should have a chemically identical environment, and this particular methyl group should have a different chemical environment in comparison to the other 2 methyl groups. So, a sample measured at a very low temperature of minus 150 degrees Celsius has 2 singlets in the ratio of 2:1, one corresponding to this particular methyl groups, which are these 2 methyl group with the intensity of 2, and this particular methyl group comes separately with the intensity of 1 because this has 6 hydrogens, this 2 methyl group, and this methyl group has 3 hydrogens. That is why the intensity ratio 2:1. Now let us take the example of 2,2,3,3 tetrachlorobutane, N-butane for example. Here the chlorine groups are fairly bulky groups, so one can freeze the rotation of this particular molecule. The carbon 2, carbon 3 bond rotation can be frozen. Under these conditions, if you look at very low temperature NMR spectrum, these are probably the 2 conformations which are going to be the most populated conformation among the various conformations that are possible, because these are the 2 conformers which are staggered conformation. Now, if you look at this conformation alone, the 2 methyl groups are chemically identical environment. They are not distinguishable because they are flanked by 2 chlorines in each case. So, if you measure the spectrum of this molecule alone, then there will be only one signal for the 2 methyl group. Similarly, if you measure the NMR spectrum of this conformation alone, there is a C2 axis of symmetry bisecting this molecule in this particular way. So, these 2 methyl groups are exchangeable by a C2 operation. So, therefore, they are chemically identical in their environment. But the chemical environment of these 2 methyl groups are very different from the 2 methyl groups here. Here the methyl groups are flanked by 2 chlorines, whereas here one is flanked by a chlorine, the other one is flanked by a methyl group. So, chemical shift wise, although these 2 are identical, These two are different from the other two which is in the other conformation. In other words, the methyl groups in this conformation have a different chemical shift environment compared to the methyl group in this particular conformation. So if these two conformations are the most populated conformation at very low temperature, then this should be even more favorable because the two methyl groups are anti, where these two methyl groups are gauche with respect to each other. So at low temperature of minus 44 degrees Celsius, two singlet resonances are seen in this particular spectrum corresponding to 2:1 ratio. In other words, this conformer population is twice as much as the conformer population which corresponds to this one. The activation barrier for the carbon-carbon bond rotation in this molecule is calculated to be about 15 kilocalories per mole. One can use various nuclei for the variable temperature NMR spectrum. We have already seen one example of the carbon nuclei being used in the variable temperature NMR spectrum of the cis-1,2-dimethylcyclohexane. Here, fluorine nucleus is used for the conformational study of this difluoro-dibromo-dichloroethane derivative. Now, if you look at these various conformations, the one where the two bromines, which are the bulky groups in this particular system, which are the farthest away from each other in this particular conformation. In other words, conformation A is going to be the most stable conformation. Conformation B and C are going to be the least stable conformation, of which, for example, C is going to be the least stable because the two bulky groups which are bromine and the two chlorine groups which are also bulky with in comparison to the two fluorines, for example. This will be the least preferred conformation and this will be the most preferred conformation. The barrier to go from A to C has been calculated using the fluorine NMR spectroscopy. The fluorine NMR spectrum, if you measure the spectroscopy at a very low temperature, you can see one signal corresponding to these two fluorine, one signal corresponding to these two fluorines, and one signal corresponding to these two fluorines here, which are chemically distinguishable from one to another in terms of A, B, C being chemically distinguishable. The activation barrier to go from A to C has been calculated by the variable temperature NMR to be about 9.9 kilocalories per mole. These are some exotic examples of fluorine NMR being used for the fluorine has fluorine 19 as an isotope, which is a spin half isotope. So it is just like a proton spectroscopy that we are talking about. Spin half nucleus is what we are talking about. There are two isomers possible for this 1,2 disubstituted derivative of this kind. This is a large macrocyclic ring, so it should undergo a rapid conformational change because of the size of the ring is fairly large. And these two fluorines are in the erythro isomer and these two fluorines are in the trio isomer. As it is in the erythro and trio, the two fluorines are not distinguishable. They are nearly identical chemical environment with respect to each other. So at room temperature, when you measure the spectrum where this undergoes a rapid interconversion among the various conformation, NMR will be able to distinguish between these two fluorines being either axial or equatorial in this particular macrocyclic system. So it essentially gives only one signal for the trio and one signal for the erythro for the two fluorine atoms, and this is essentially seen at room temperature. When you cool it to very low temperatures of minus 75 in the case of erythro and minus 92 in the case of trio, the signal splits into two singlets because these two fluorines are now distinguishable with respect to each other. So one can see two fluorines separately. One probably corresponds to an axial kind of a position, the other one corresponds to an equatorial kind of a position. Similarly, in these molecules also the two fluorines become distinguishable, and that is the reason you see two signals here. This has been theoretically calculated as the number of various conformations that are present in this molecule. If you look at this particular conformation where the two fluorines are given the magenta color, the cyan color, the two fluorines are indicated by the cyan color. In this conformation, the two fluorines have chemically different environment, and this is the most stable in terms of the relative energy being 0 kilocalories per mole. This is 2.81 kilocalories higher energy compared to this conformation 3. Conformation 1 is about 3.72 kilocalories higher energy compared to conformation 3. So in conformation 3, the two fluorines are different, and that is why at low temperature one sees these two fluorines separate signals. At room temperature, there is a rapid interconversion among the various conformations, so the two fluorines become indistinguishable at a higher temperature. Same is the case with the kind of the trio isomer also. The two fluorines have distinctly different chemical environment at low temperature. This is the lowest conformation energy. Compared to the other conformers, this would be highly populated at low temperature. So the two fluorines are different in chemical environment. So two signals at low temperature. At high temperature or at room temperature, there is a rapid interconversion of these various conformers. So the two fluorines become indistinguishable. As a result, there is only one signal that is present in the high temperature NMR spectrum. Now this is a propeller shaped molecule. This is called a tryptophan, tryptosine, not tryptophan. This molecule is called a tryptosine, and this is a propeller shaped molecule, for example. In this molecule, when you put a substituent here, that substituent is hindered from rotating freely by these three hydrogens which are indicated. In other words, cartoonic representation of this molecule is shown here. This is a conformation of the molecule. You can see very clearly that the nitrogen substituent that is present in this cavity, the free rotation of the nitrogen is going to be hindered by the bulky groups that are being present in the nitrogen interacting with these three hydrogens which occupy these positions. So the rapid rotation of the carbon-nitrogen bond is not possible in this molecule. That is one process. The second process is the nitrogen can also undergo inversion, pyramidal inversion. The lone pair is down here. The lone pair can also become up by the pyramidal inversion. So this is essentially a propeller shaped molecule where the carbon-nitrogen bond has a restricted rotation in this molecule. This has been studied by NMR spectroscopy. Now if you look at this molecule, this would be a chiral molecule if this is conformationally frozen in this particular state. The reason being there is no plane of symmetry or there is no SN symmetry present in this molecule. So as it is, the molecule is chiral in the frozen conformation like this when there is no rapid carbon-nitrogen bond rotation. So these two CH2 hydrogens, these two hydrogens on the CH2 become diastereotopic in nature. So we are looking at the CH2 hydrogens of this molecule at low temperature when there is no rapid rotation of the carbon-nitrogen bond. Because of the chiral environment that is present in this molecule, this CH2 appears as an AB quartet because CH2 is a diastereotopic hydrogen in this particular system. When this becomes rapidly interconverting in terms of the carbon-nitrogen bond rotation being very high at a higher temperature, in other words at minus 49 degrees Celsius or so, the carbon-nitrogen bond becomes rotatable easily. At those temperatures, the CH2 is no longer distinguishable and you just to see a singlet for the CH2 hydrogen in this particular molecule. And this is a simulated spectrum putting in these rate constants corresponding to various temperatures. One could easily simulate the spectra that is shown in the experimental side, which is this side, and this is a simulated spectra. Based on the variable temperature NMR spectrum, the activation barrier for this particular process has been given in this table as 11.6 kilocalories per mole for the N-benzyl derivative, and for the N-methyl derivative is about 9.2, slightly smaller when that is a N-methyl group in this system. One can also look at it from the carbon-13 NMR spectroscopy point of view. These are the quaternary carbons labeled as QC. There are three quaternary carbons in the front, 1, 2 and 3. These are the quaternary carbons. The back side also there are three quaternary carbons which are aromatic carbons, 1, 2 and 3. If this molecule is truly chiral at low temperature, one should be able to see these three carbons separately, and the backside three quaternary carbons also one should be able to see it separately. So this is what happens at low temperature when the spectrum is assured at minus 160 degree Celsius. There are 6 carbons that are seen corresponding to carbon number 1, carbon number 2, carbon number 3 which is in the front, carbon number 4, carbon number 5, carbon number 6 in the backside, which essentially constitute the 6 lines that you see in the carbon-13 spectrum of this particular compound. If the molecule is undergoing a rapid rotation and the chirality is lost as a result of that, then all the 3 carbons in the front and the 3 carbons in the back should come as single signal. So essentially you see 2 signals, one corresponding to the carbons in the front, the other one corresponding to the carbons in the back side of the molecule, which are these 3 carbons which are present. When the chirality is removed by putting 2 identical groups on the nitrogen, this is a N-diethyl group, whereas the previous example is N-methyl N-benzyl group, and that is what makes this molecule chiral. The chirality is removed now, so essentially what you see is the 2 methyl groups, the 2 hydrogens on the methylene group essentially appearing as a simple quartet in this particular case, And when this molecule is in frozen state, there are two conformations possible. The methylene group can be either in this position or it can be in this position also. So two different environment is what is seen for the methylene, which is seen by the two humps that are seen. It is not at fully its temperature is not low enough, for example, to completely freeze out the molecule. So that is why you see broadening of the line. If it was possible to measure the spectrum even at low temperature, perhaps one would see two quartets kind of a system is what one would see in this particular case. So the two methylenes become indistinguishable and become a single signal at high temperature. At low temperature, these two methylenes are possible to distinguish from one another because of the pyramidal inversion that is taking place. The activation barrier for this process is about 8.1 kilocalories per mole for the rotation of the carbon-nitrogen bond in this molecule. Here is another very interesting example of an 18 aniline molecule. Please recall the anisotropic effect of aromatic ring current effect. This is an aromatic molecule because it is an 18 aniline molecule corresponding to 4n plus 2 electron system. Now there are 6 hydrogens in the cavity of the molecule and there are 12 hydrogens on the periphery of the molecule. So if this is truly aromatic and planar in nature, these 6 hydrogens should be highly shielded because they come in the shielding zone, whereas these 12 hydrogens should be highly de-shielded because they come in the de-shielding zone of the ring current effect anisotropy of this particular molecule. However, the molecule is big enough to undergo conformational change. In other words, if you rotate this carbon-carbon single bond, this hydrogen can be brought in and this hydrogen can be taken out. So the hydrogens which are originally inside can go out, and the hydrogens which are originally in the outside periphery can also come inside, 6 at a time. So there is possibility of a rapid interconversion between the inside hydrogens and the outside hydrogen. So if such a process is taking place very rapidly, NMR won't be able to distinguish between the hydrogens which are inside and the hydrogens which are outside. In fact, when the spectrum is measured at plus 110 degrees Celsius, a sharp singlet is what is seen in the molecule for all the 18 hydrogen. There are no other hydrogens which are distinguishable in this molecule. The inside-outside process, in and out process is what is taking place rapidly by carbon-carbon bond rotation. So as a result, one sees all the 18 carbons as a singlet in this particular system. Now see what happens at low temperature when the spectrum is measured at minus 60 degrees Celsius. At minus 60, the molecule is frozen and it is probably in the planar most stable conformation because it is an aromatic system. If it is non-planar, of course, it will not be aromatic. In fact, it probably goes through a non-planar transition state when it is undergoing a rapid interconversion of the inside hydrogens going out and the outside hydrogens coming in. Now, at a very low temperature, when the molecular conformation is frozen in this particular fashion, the inside hydrogens can be very clearly seen at minus 3 delta ppm, which is this signal here, as a multiplet. And the outside hydrogens, which are the 12 hydrogens, can also be seen around 9.5 ppm also delta. So this is a highly de-shielded hydrogen, aromatic hydrogen. This is a highly shielded hydrogen, which is also aromatic, but it is in the core of the aromatic unit in this particular case. Now there are 12 hydrogens in this particular multiplet and 6 hydrogen in this particular multiplet. So one has to take an arithmetical average of these, a statistical average of these two, not the arithmetical average. A statistical average of these two chemical shift values to attain the chemical shift value of the averaged out signal, which is this particular signal. In between, you can see there is a large uncertainty associated with the determination of the chemical shift value. Particularly if you look at plus 40 degrees Celsius, the uncertainty is so much that you don't see any signal also. You just see a flat line NMR for this particular spectrum, for this particular compound. The uncertainty is so much so that you don't see any signal at plus 40 degrees. This is a scenario which is an interesting scenario, that you measure an NMR spectrum and you don't see a signal in spite of the fact there is a sample that is present, because of the uncertainty principle essentially wipes out the signal to be a flat line in this particular case. Another example, a very similar example to the cyclohexane system that we talked about. This is a cycloalkyne. It's a strained system. The molecule is not planar as it is shown. The molecular conformation is a C2 symmetric conformation, which is a chiral conformation. The molecule can undergo C2 kind of a, this is also C2 symmetric and this is also C2 symmetric, and they are mirror images of each other. They can undergo rapid interconversion by this carbon coming down and this carbon going up, which is the conformational change that we are talking about in this case. and such a conformational change would make the molecule look like this one in the transition state. If it were to this conformation, this has a planarity associated, plane of symmetry associated with the molecule. So this is achiral transition state. So at 145 degrees Celsius, for example, this molecule sort of NMR point of view looks like this, and all the methylene hydrogens are equivalent. So you essentially get a singlet at high temperature. At low temperature, if it has to be a chiral conformation like this, these two hydrogen will be diastereotopic because this is a chiral molecule. So diastereotopic hydrogen. These are enantiomers which are indistinguishable. Nevertheless, within the enantiomer, one of the enantiomer, this CH2 would be a diastereotopic hydrogen, which is identical to this CH2 because of C2 symmetry. So such a diastereotopic hydrogen gives a AB quartet, which is nicely seen at 58 degrees Celsius or so. So at room temperature, when you measure the spectrum, this is what you are going to see, essentially AB quartet for this molecule, because it is a chiral conformation that we are dealing with in this particular case. This is another standard textbook example of a restricted carbon-nitrogen bond rotation in amides. N,N-dimethyl formamide is discussed here. Now, because of the participation of the nitrogen lone pair on delocalization onto the oxygen, the molecule attains a sort of a double bond character between the carbon-nitrogen bond. Because it has a double bond character, its activation barrier for free rotation is fairly high. So this molecule does not undergo free rotation at room temperature. Activation barrier calculated from the variable temperature NMR spectrum is about 22 kilocalories per mole. So at room temperature, this molecule can be giving two signals corresponding to the red methyl and the blue methyl. The red methyl is cis to the oxygen, the blue methyl is trans to the oxygen. Chemical shift environment wise, this will be different from this particular methyl group. So as a result of that, this molecule essentially, under the conditions of room temperature, will give two signals for the two methyl groups, and you see two signals at room temperature around 35 degrees. You see two signals, one that is next to the oxygen, cis to the oxygen, probably this particular signal. The one that is trans to the oxygen is probably this particular signal here. And if it is going to undergo a rapid interconversion, these two methyl groups will interchange its place. The blue now has become the cis to the oxygen, and the red has become the trans to the oxygen. If such a rapid interconversion was to take place, the coalescence will take place, and these two methyls will essentially appear as a singlet. In fact, at 170 degrees Celsius, the molecule shows a singlet for the two methyl groups. So because of the restricted rotation having this kind of a barrier, you have to heat up this sample to high temperatures before coalescence can take place. So the coalescence temperature is roughly 123 or so, because you can still see two peaks in this region here at 18 degrees. So the coalescence takes place around 120 degrees or so, which is corresponding to the coalescence temperature. Above the coalescence temperature, you have a sharp singlet, and below the coalescence temperature, you have two signals corresponding to the two methyls, which are indicated by color coding. Here is the last example of this particular lecture. We are talking about again a restricted rotation of the carbon-nitrogen bond. This is a trinitro N-methyl aniline is the molecule. Trinitro N-methyl aniline, there are two hydrogens in the aromatic unit. Suppose if there is a restricted rotation around the carbon-nitrogen bond, if the molecule can be represented like this, then these two hydrogens are no longer in the same chemical environment. It should be possible to distinguish them. And if there is a coupling between these two hydrogen, which is the meta coupling, so this should be a doublet, and this also should be a doublet due to the meta coupling in this particular molecule. However, if there is a rapid rotation of the carbon-nitrogen bond, these two hydrogen chemical environment will average out and it will give only a singlet. Indeed, at room temperature, you do see only a singlet, but at a very low temperature, when there is restriction of the carbon-nitrogen bond rotation, this methyl group in this nitrogen makes this hydrogen and this hydrogen distinguishable chemically. So what you see is an AB quartet corresponding to the meta coupling between the AB system, which is this coupling that we are talking about. This is a simulated spectrum based on the computer simulation using this kind of a lifetime of this molecule for the various rotational rate constant is what is the inverse of this will be the rotational rate constant of the process that we are talking about. So we are not done with the dynamic processes of NMR. In the next module also we will continue with the dynamic processes of fluxional molecule and certain organometallic examples of the molecular dynamics by variable temperature NMR. So see you in module 14 and continue with this lecture in that particular module. Thank you very much for